So hopefully by now what you've done is you've rolled the dice a couple of times and found the sums of that. If you only do about 20 rolls or so, you get a pretty random amount of sums available, right? You might roll 8 a couple of times. You might not roll 4 at all. Okay, so at about 20 kind of rolls, you get this weird kind of random thing. And if we were doing this in class, we would see that everybody would have very different histograms. Okay, and that's great. But then when we add all the data together and maybe we get to 100 rolls, right? That's a sum of 100 rolls of dice. We might see something just a little bit kind of more regular. We might see another shape kind of emerge. And as we increase the number of rolls, we can get to a place where we kind of see the same shape kind of stay, right? And so hopefully you did that. Hopefully you rolled the dice 20 times, got something very random, and then, you know, did the simulation and saw that as the number of rolls of dice increase, after, I don't know, a couple hundred rolls, the shape doesn't change very much. And what you get is a shape that looks like this. Like if we were going to do a frequency polygon instead of, right, and smooth it out instead of a histogram, we would get a shape that looks like this. And this shape shows up in a lot of different kind of data when you start to map it out. We see it kind of everywhere, and your notes mention a couple of those things. You know, your notes mention that height of people follows, you know, if we took everyone or took a huge sample of people and measured their heights, and you know, and we might want to do this kind of regionally as well, like in Canada or something, we would see, you know, very few very short people, very few very tall people, and a whole bunch of people in the middle. Okay, the same thing with shoe size, or kind of a whole bunch of things show up in this way. And what we get out of this is we get something called a normal distribution. So, you know, in all of your other classes, you might say, well, you know, what's normal? Nobody's normal. Well, in math, actually, normal is a very specific set of criteria. If you meet that criteria, then you are considered normal. So our normal curve is a symmetrical curve, right? Meaning that, you know, it has this symmetry in it. If I put a mirror right here along this line, I'll see the reflection of it, you know, will be the same as what's behind it. So we've got this symmetry here. And it makes a shape called a bell curve. Okay, so, you know, if you take university classes and the professor curves the marks, this is kind of what they're doing. They're saying lots of people should have average marks, only a couple of people should have very high marks, and only a couple of people should have very low marks. So they take all of the marks and they might distribute them along this curve, this normal curve. So that's what they're kind of talking about there. It can be very helpful if you do pretty bad on your geochemistry final, like I did, and your mark gets bumped up because of the curve. So it can be pretty helpful and pretty powerful if you can understand it. All right, so the distribution of that is what we see in this picture, okay? And it represents a unimodal symmetric distribution about the mean. So what that means is we've got, you know, one measurement of data. Our data is being measured in one way, and the mean is in the middle here. So always the mean is right here. This is our mean, and here we're using mu, but remember, differentiate between those two. So if you're going to see mu or you're going to see x bar, we are going to use the two interchangeably. That will not be the case if you take university stats or college stats. Okay, so be careful of that. But in our course, just an introduction to stats, we're gonna use those two interchangeably. So our mean is always in the middle. Okay, a couple more things is it only has one hump. Okay, so there's only one bump in our data. Okay, the mean, median, and mode all fall really close to this middle value here. Okay, so this is our mean, but our median, we want our median to be very close to this, and we want our mode to be very close to this. And if that's the case, then we have normal, we have, kind of met the condition, one of the conditions of normal data. So we've got the curve is symmetrical. The area under the curve can be considered equal to 1. So it's 100% of the data falls under this curve. Okay, so we can see if we add up these numbers here, 2.35, 13.5, 34, 34, it doesn't quite get us to 100%, because there's very, very, very few pieces of data way out here in the edges. But because it's this curve, reaching out to the furthest reaches of the curve is going to represent all of the data. Okay. And so we want to remember that 1 as a decimal equals 100% as a percent. And I know you know that. I know that's very obvious, but we kind of forget that sometimes. And we're going to look at these questions in terms of decimals sometimes and percents sometimes. So we just want to be really careful that we remember that. Everything under the curve needs to add up to 1, which is 100% of the data. Okay, another key feature here that would make this normal, that would make this shape. Where does this shape come from? Well, 68% of the data falls within 1 standard deviation, and that's what's going on here. So you put your mean in the middle, and then you add up 1 standard deviation, and you subtract 1 standard deviation. So again, if your mean, the mean is 10 and the standard deviation is 2, that would mean that 68% of the data, right, more than 2/3 of the data, would fall within 8 and 12, which is +1 and -1 standard deviation. All right, then we would add more. Okay, so to kind of go beyond that, within 2 standard deviations, so we would take another 2 off here, add another 2 here. Within this area here, we want to have 95% of the data, right? Because that means most of the data is concentrated around the middle, right? And that's what we see when we're rolling dice. What happens most often is 7. 7 shows up most often because there's the most amount of ways to make 7. But you know what? 5 shows up every once in a while, and 9 shows up, and so there's other things that show up quite regularly when we roll dice. When we kind of go beyond those 2 standard deviations and we go to 3 standard deviations, so again, if we're keeping our example of a mean of 10 and a standard deviation of 2, that would mean that, oops, sorry, I have to add 2 here. That would mean that 99.7% of the data falls between 4 and 16. Okay, whatever we're measuring, right? We're just taking a random example here. So, I don't know, let's say shoe size. That's a terrible thing, but I don't think there's 16 is even a possible shoe size. Maybe it is. But just say, the average was 10. Most people have between a size 8 and a size 12. And then more people, as we expand the range beyond that average, right, to 2 standard deviations away from the mean, we include more people, and then we get more people. And then there's very, 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 very few people that would have size 2 or size 18 feet, if that is what our example means. Okay, so that's how this works. These are kind of rounded decimals. If you go on the internet, you might find slightly different numbers. You might find more or less decimal places out there. These are the numbers that we're going to use, and I encourage you to refer to this chart and not find one off of the internet to use, because we're going to get slightly different answers here. I won't see your source of information. Okay, so this is kind of out of the textbook, out of the curriculum document that we have access to, and it's it's very reasonable data. It's very normal, right? This 68, 95, 99.7 is very commonly used representations of normal data. Okay, so what does this mean? Well, how can we answer some questions? Okay, well, and first, actually, let's take a second and see where we see this. So this pattern in data shows up often enough that we call it normal, right? And we see it all the time, kind of in natural situations and human created situations as well. Heights of individuals, again, we talked about that. Weight of individuals, most people are average. Very few people are way too skinny or way too big, right? Whatever that means. But we see that a distribution, a normal distribution. IQ scores of individuals, most people are average. Very few people are geniuses, right? Would exist on that really high number of standard deviations away from the mean. And very few people have very low IQ scores as well. Amount of rainfall in a region. If you look over, a period of time, you can look for, what is normal, what is average, and then you're going to have years that are very wet and years that are very dry. Some years that are kind of dry, some years that are kind of wet, and then that, that kind of middle ground. Life expectancy of automobiles, you can see that again. It follows that same kind of pattern. And actual mass of material in commercial packaging. So if you buy a 500-gram bag of chocolate chips, it's pretty unlikely you have exactly 500 grams of chocolate chips in there. You're going to have, maybe a little bit less, maybe a little bit more, but most of the time it's going to fall about that average. Okay, it's going to be about that middle. So how can we answer some questions? Well, I'm going to give you my notes. My notes are slightly different than yours. So here's my example one. Curve A and curve B are both normal curves, right? And why are they normal? Well, they've got one hump that's in the middle. It's symmetrical, right? They've got one hump, and we can see that, excuse me, most of the data, 68% of the data falls within one standard deviation, right? And we see this nice kind of one hump. Now, it doesn't mean that they all make exactly the same shape, right? We can have kind of a short normal curve. We can have a really spiky normal curve. And really, this just comes from changing our scale. So if I switch my scales around, I can probably make these guys look more similar, but I just want you to see that it doesn't necessarily have to be that perfect bell curve that we saw in the last question. We can kind of change our scale and make the shape look slightly different. But again, both of them still have that symmetry and that one hump and that concentration of data in the middle. Now, what's the mean and standard deviation? Well, for curve A, remember that okay, so our mean, let's call it mu, equals 75, right? Because it's the value right in the middle. Our standard deviation, sigma, is, well, we can see that we're going up 1, up 2, up 3 on our curve here. We can see a standard deviation is 10. Okay, so that's how we can read this curve. In curve B, we've got, again, our mean is in the middle. Our standard deviation, or sorry, our mean, we'll call it mu here, is 75. Our standard deviation, however, though, is smaller. We've only got a standard deviation of 3 because we're going counting up by 3s. Okay, and likewise, we're counting down by 3s from our mean. Okay, so I mean that would account, the different standard deviations would account for the difference in shape for these guys. Okay, next question. Well, and actually your notes ask you to draw a normal curve that has a mean of 20 and a standard deviation of 5. So can you recreate a picture that looks like this that has those data points? Okay, so I encourage you to try that. All right, let's take a look at example 2. We've got a histogram here that has the age of harvested trees. So is that normally distributed? Okay, well, let's take a look. First, let's look at the shape. Does this look like a bell curve, right? If we were going to smooth out these bars, does it look like a bell curve? Well, it absolutely doesn't. So, doesn't have kind of one hump, right? It has like 1, 2, 3 humps. So already it's not looking like it's normally distributed. If it was normally distributed, you know, we made those, think of the histogram that you had for 1,000 dice rolls, right? It was still a histogram, it was still kind of blocky, but it had just kind of one rise up in the middle, okay? And so also there's no symmetry here. So that's another kind of strike against it being distributed. I can't put a mirror here and have the same picture on both sides of the mirror, right? Whereas I would if it was a normal curve. All right, so that's, I mean, those are good reasons, but they're not very mathematical. So let's kind of take a look at some of our data. The mean of the data, so if I use my table here, the mean is 26.84, and our standard deviation is 7.38. Okay, so I did that in my calculator, and those are the values that I got. Hopefully you get something very similar in your calculator as well. So let's take a look at what would happen one standard deviation away from the mean. Okay, so the mean plus 1 standard deviation, so 26.84 plus 7.38 is 34.22, and 26.84, our mean, minus a standard deviation is 19.46. So in that range of values between 19.46 and 34.22, how many pieces of data do I have? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, not 19 doesn't count, 10, 11, 12, 13, 14, 15. 15 pieces of data. Oh, no, this one doesn't count, sorry. 14 pieces of data. Okay, so I have 14 out of 25 pieces of data fit in that. So 14 out of 25 is 56%. Now remember, according to our normal distribution, 68% of the data needs to fall within 1 standard deviation, but only 56% here does. Okay, so 56, not 68% of the data is within plus or minus 1 standard deviation. Okay, so these are now, we have a good kind of mathematical proof that this is not normal data. Okay, so 56% is not close enough to 68%. If we had done this and we got 66%, I would be convinced that this might be more normal. But 56% is very far away from 68%. So we have to kind of use our judgment here. And I know you don't have a lot of experience doing this yet, so it's kind of hard to know. There's kind of more math behind it, but we're not going there. 56% is just too low compared to 68%. Okay, so I hope that part makes sense. I really encourage you to read through those notes again, maybe watch the video again.